Hi everyone, good afternoon. Welcome to our talk. My name is Govind and with my colleague Anshul, I'll be giving this talk and the main topic is challenges and solutions for the physical layer assisted security framework in flying ad hoc network. So physical layer security is not a new term and this has been there for a while. A lot of literature is available, but there is no real-time implementation exist, or there is no use case implementation of physical layer assisted security available today. So why we are giving this talk? Because as part of our applied research, this is one of the key area, and we try to implement some of the available literature, and we saw a lot of challenges, we saw a lot of constraints that was being assumed. So we thought like how to mitigate them one by one. So in this talk, we'll be briefly then talking about the challenges and some of the probable solutions or the direction we can have the implementation of the physical layer assisted security framework. It can be in a flying ad hoc network, or even it can be in any IoT devices or in IoT ecosystem, be it consumer, industrial, or it can be infrastructure. Okay, so this is the high level agenda and outline of the talk. So we will start with introduction and motivation, then we'll give brief introduction on the physical layer security, and then we will review the implementation challenges for PLS. Then we will be briefly talking about the different kind of capturing monitoring framework we have with the off-the-shelf commercial Wi-Fi hardware platforms, and then the conclusions and the future work and the roadmap we have ahead for the implementation. Okay, before I start why we are doing, what are the challenges, let's briefly introduce about ourselves. So we are part of Secure System Research Center, which is a applied research division of Technology Innovation Institute in Abu Dhabi. And what we do, we basically drive end-to-end security from top to up. So when down to top. So when I say down to top means we basically drive from root of trust, secure boot till application security, middleware security, and network security. Our group in SSRC is Secure Comms Group, which is basically focusing on network security, which is like short range, long range, wireless security. And we basically mainly focus on resilient and long range wireless communication with low latency. And we basically don't do theoretical research, rather we believe in doing, and we basically focus on applied research with real world applications. So what are our use cases, right? Why? So just to give you some direction, so let me quickly explain about our use cases. So we have two use cases. One is human-to-human communication use case, which is essentially phone use case. So in that case, you can have chats, emails, video conferencing, and other use cases, machine-to-machine use case, in that we can have telemetry data, control command, video streaming, and the latency-sensitive data. So what we are doing in this use case, what is our contribution in this use case? So we are building a secure wireless mesh core network, which is connecting a lot of nodes in both of the use cases. And in this mesh connectivity, so we have larger number of nodes in this infrastructure. So all are point-to-point communication. So we have edges and we have fog nodes. So the edge nodes, essentially the communication link is Wi-Fi, Bluetooth 15.4 and other short range communication protocol. And for fog node, the cloud connectivity through secure gateway, we have LTE as backhaul. So, and we basically are using the open source components for very obvious reasons. Like, this ecosystem is really good and you can easily scale up things, and anyone can contribute. And what we are doing, so we are taking the base open source component for a basic building block. On top of that, we are adding our own specific value add with respect to the security component within the network stack. And we are introducing ML-based new schemes, prototyping those schemes to adding the defense mechanism between these nodes. And then we have dynamic radio management with multi-radio and so that we can do various band management. We can do in a single band frequency hopping, adaptive frequency hopping. So these are some of the schemes. So in this infrastructure, the physical layer security is mainly used for mutual authentication and continuous authentication between two nodes. So that is the main, the high level overview. So now I will hand over to my colleague Anshul to give you just basic introduction on the PLS. Why PLS? What is PLS?
Thank you, Govind, for highlighting all those aspects on which we are working on, different use cases. So as we know that the recent developments which have happened in the domain of embedded systems and also in the wireless communication technologies have basically driven a lot of applications, machine-to-machine applications and even human-to-human applications. So what are our two main use cases on which we are working? One is the machine-to-machine communication. For that specifically we are looking into drone-to-drone communications, and then we have a phone use case where basically there will be some sort of sleeve sort of thing. So that will basically help us to make the phones independent of some sort of communication technology. But in this talk we will be mainly highlighting on the drone use case. So this we have chosen because the drone use case is more challenging for implementing physical layer security solutions. Means in any ways physical layer security solutions, there are a lot of work which have been going on. It started sometime I think in 2010 to 12, but mostly it's in academic. From the implementation point of view, we can find a very the works which exist are very limited. So we just try to explore these things on this. So on the UAV communication, so why we have chosen this UAV use case? Because as you know, UAV basically can revolutionize the whole communication infrastructure, because we are able to deploy a communication infrastructure in some place where it is very hard to reach or deploy the traditional communication infrastructure. So UAV provide us that ability. So that is why they have seen a lot of applications. For example, disaster management, we can these UAVs can easily go and create an infrastructure and perform different operations to such as rescue operations and all those operations. Then we have military services. So everyone is aware how these drones are basically changing even the warfare. Each and everything is being changed. Now we are getting UAVs. With UAVs, you can just it's just change everything. We need to think carefully. Then we have, and then they can also perform the operations of real-time and remote surveillance. So that is an obvious application of these UAVs. So they can also be beneficial for the agricultural purposes. And Amazon, as we all know that companies like Amazon are already thinking or even using these drones to deliver the packages. So they provide a lot of applications. So that is why everyone is jumping onto this, and even these UAVs based infrastructure is one of the prominent use case which we are looking for 6G and beyond communication networks. So although we have a lot of benefits with these UAVs, but there comes a lot of security challenges which we need to address before actually deploy them, because some of the applications in which UAVs will be used will be life-threatening. So next, UAV security. So traditionally we are using cryptographic approaches, both symmetric and non-symmetric framework. So in crypto, it's difficult somehow in case of UAV communication to deploy such security infrastructure, the existing one cryptographic based, because of the following reason. First, in case of UAVs, we have a very limited amount of energy and also the computational capability. So when we deploy such solutions based on cryptography, they may consume a lot of resources, and we don't want to happen it. So second is the dynamic and the ad hoc topology. So we know that since the UAVs will be moving, there will be a swarm of UAVs and they will be moving in different directions. The topology will be highly dynamic in nature. So it will be very difficult to create some sort of a key distribution center to manage to distribute those keys. And even if we create those keys, the distribution will mainly happen on the over the air wireless channel, and that is always vulnerable because on the wireless channel we are always transmitting the information on the broadcast way. Next is the presence of an adversary with adequate computational capabilities. There may be a use case of UAV where there may be a nano drones use case. So in that case, if they are using these cryptographic keys, so what may happen that the adversaries may have computational capabilities which is even greater than the computational capabilities which are used at the legitimate users. So it may then pose another threat that they might be able to break those encryption. Next, so again, the communication infrastructure of UAV. So suppose there is a UAV base station, so it will be communicating with the ground through a line of sight links. Then we have a shared frequency band. So most of these UAVs will be operating over the frequency bands like 2.4 gigahertz. So, and where a lot of users are already operating upon, and then these UAVs can be easily detected with some sort of radars and all those things. So these three factors makes them easily more susceptible to jamming and eavesdropping attacks. Then we have a very constrained network, suppose a nano drones use case where a large number of small drones may be deployed to accomplish some mission. So since they have very low computational capability, so it will be difficult for them to run those complex encryption and decryption algorithm. So all these things basically generated a need that there should be something which could assist the existing cryptographic infrastructure which is already available. I am not saying that it will be going to replace that or it can be an alternative, but it can always assist that. So for that, we can use the physical layer security solutions. So where basically we will be looking some of the physical layer features to generate security solution, and it's simply signal processing. So we are not posing a much overhead on the resources side. So as I said, physical layer security, so we just want to use the physical layer, the characteristics of the physical layer, our random channel, to design some sort of security solutions. So what it does, so in physical layer security, so we know that if suppose two users wants to communicate, suppose Alice and Bob wants to communicate, so they will be communicating over the wireless channel, and when we transmit a signal over the wireless channel, the channel is completely random in nature. So we can harness this randomness to design some sort of security solutions. Then apart from the channel characteristics, we can also use some of the imperfections which are there on the radio front end, and also on the device level imperfections which basically get incorporated into the device during the manufacturing process, which is also refers to as physically unclonable function, PUFs. So all these things we can take into account, the channel based feature, the device based features, and even the features which are there or the imperfections, what we say in case of RFF front end to design some sort of security solution. We can actually use the uniqueness which is associated with these features to design the security solutions. Another thing is that the physical layer security can guarantee perfect security. So I will elaborate on this, how it can be done in the next. And the most interesting thing is that they basically operate independently of the existing cryptographic infrastructure. So we can always implement them without interfering with the existing infrastructure. So next, what is physical layer security? So if we go on to the basics of communication theory, suppose we have three nodes, Alice, Bob, these are our legitimate users, and we have an eavesdropper, which is an adversary or a malicious user. So Alice wants to transmit some signal to Bob, and an eavesdropper is there. He is listening, he is overhearing that information. So the basic principle which we deploy in physical layer security is that we use a simple principle that if we transmit at a rate that is greater than the channel capacity, instantaneous channel capacity, then we will not be able to decode that information at the receiver with a reasonable errors. Means the error will be very high if we transmit at a rate which is greater than the channel capacity. So this principle we are basically using to design physical layer security solution. So in this case, we see that we have a legitimate channel that we can call the channel between the Alice to Bob, and the wiretap channel, which is the malicious link between the Alice to Eve. So when Alice broadcasts some information, so that anybody can hear. So if the channel condition or the instantaneous channel capacity between the Alice to Bob is greater than the Alice to Eve, the channel capacity between the Alice to Eve, and we transmit at a rate that the Bob is able to decode that information. However, it is not possible for the Eve to decode that information because that rate is much greater than the channel capacity between Alice to Eve. So we use this principle to basically use, this is basically the principle of physical layer security. So we are using this, exploiting this principle. So now this is basically the channel based features. So in other words, we can simply say that we somehow needs to improve the channel capacity. For deploying the physical layer security, the channel conditions for the legitimate users must be better than the channel capacity for the malicious users. So the obvious question comes, what if the eavesdropper is very close to the Eve, very close to the Alice? Then in that case, the eavesdropper will have a much better channel condition as compared to the Bob. So we cannot deploy physical layer security, but it doesn't, there are certain solutions which we can use in this case also. For example, we can use dedicated jamming, and that the jamming should be done in such a way that it should be in the null space of our legitimate user, that is Bob. So when we deploy jamming, and that jamming signal basically interferes with the Eve and it degrades the signal to noise ratio at the Eve, and in this way we are basically degrading the channel quality of Alice to Eve in compared to Alice and Bob. Similarly, we can use other solutions like beamforming, and then we have we can harness the benefits of diversity. So there are a lot of solutions by which we can even deploy physical layer security for the scenarios where the eavesdropper has a much better channel condition than the legitimate users. So this was basically the information theoretic point of view. In one word, if we want to say that the objective is we need to make the mutual information between the Alice and Bob as 0. So, and so there are features like, as I already said, so we have channel based features. This feature, the channel between Alice to Bob is completely random. And another important fact is that since Alice to Bob channel is also random, and Alice to eavesdropper the channel is also random, and we can assume that both the channels are completely independent of each other, provided Bob and eavesdropper are at least separated with each other at a half of wavelength, the wavelength at which we are operating. And since we are operating at gigahertz of frequency like 2.4 gigahertz or even 5 gigahertz band or even much higher, so in that case the separation comes out to be in centimeters, and that is practically feasible. Means we will always have a scenario where the user is sufficiently far apart from the so we can easily use this assumption. So that assumption holds very well. So what we can say that each channel is unique, and it's completely different from the other channel apart from the random. So we can harness this what we can say, this feature to design some sort of symmetric encryption framework also. So what are the best possible use cases where we can use? So physical layer security presently is best suitable for our IoT use cases where our small low-end devices do not have enough capability to run those complex encryption and decryption algorithms. So in that case, we can design those physical layer security solutions, or we can implement them. And this also provides one of the best use case for the case where it's very difficult to have a central authority, something like that, where it's very difficult to deploy some sort of a key distribution center. So in that case, we can use physical layer security. Although there is a limitation with physical layer security also at present, physical layer security is valid only for the point-to-point communication. If you are thinking that it can be expanded to on the network, on the whole network point of view, so it's difficult. So presently, most of the solutions are valid only for point-to-point communication. So keeping in this point, we are basically looking into the physical layer security solutions to design the following solutions like mutual and continuous authentication. So as I already pointed out that the channel between each two communicating entities are unique. So we can harness this features, the channel feature, the uniqueness in the channel feature, and also the imperfections which are there on the RFF front end, like we are using simple our local oscillators. So they have inherent some clock drift. So these clock drifts are also unique in nature. So we can even exploit that thing. Then we have some device specific features like the physically unclonable function. So those can be exploited. So all these features are can be basically exploited to generate some sort of fingerprint either associated with a device or with a link. So that can be used for mutual or for performing mutual and continuous authentication. Then we have phi assisted key generation. So since we know that Alice and Bob, their channel is unique, and there is another factor which we call as reciprocity principle, which says that what Alice will see its channel to Bob, the Bob will also see the same channel to Alice, provided this in a given time frame, and that time frame is called coherence time. So if the communication exchanges happen between Alice to Bob and Bob to Alice within a given coherence time, the Alice to Bob channel and the Bob to Alice channel both will have the same response. So we can use this feature to independently generate secret keys at both Alice and Bob without requiring any third party. So that can be used to generate some sort of security symmetric key framework. Then we have anti-eavesdropping solution. So we can use for anti-eavesdropping solution, what we can use, apart from jamming and all those solutions which exist, a simple solution is we can perform some sort of bit scrambling. Like in case of OFDM systems, it is very essential that the bits, the information, the symbols which we are transmitting are perfectly mapped, and how they are basically mapped, it should be aware at the receiver side. Even if one or two of the symbols are not, they got misplaced or the receiver is not able to identify, then it results into severe degradation of the SNR. So we can even perform this simple, this what we can say bit scrambling thing to design some sort of pre-coding scheme to basically design some sort of anti-eavesdropping solution. Because if the pre-coding scheme, how we are doing that bit scrambling, that is available only with the legitimate user. So if somebody is even listening to that information, he will not be able to decode anything. And one important use case of physical layer security is, suppose there are some informations which can always be beneficial, they don't lose their value after time. So in such cases, physical layer security can be much beneficial than the cryptography. Like suppose if I am storing some information and later on by some hit and trial I got the key, so I will be able to decode that information. But if I am using physical layer security, I am deploying that solution and I am satisfying that condition, that the channel condition between Alice to Bob is, or the legitimate receiver is much better than our wiretap link, then the eavesdropper will never be able to decode that information. Because even if it's able to decode that information, the probability of error would be always greater than 0.5. So for every 2 bits, 1 bit will be wrong. So he will not get anything. So in those type of scenarios, it is very beneficial. So keeping in mind, at TII, we are doing research on our own. We are driving some of the research in this direction of physical layer security and looking how to implement them. Apart from that, we have also multiple projects which are currently going on in partnership with Khalifa University. These are some of the projects, and we are looking to use this physical layer security to design authentication, encryption, and also for radio resilience. So next, a little bit we searched to the best of our knowledge. We have did a thorough survey from the specifically looking how much work has been done from the implementation side. So we could find the following works which have basically used physical layer security for continuous authentication, even for secret key generation, Sybil attack detection, and anti-eavesdropping solution, secure pre-coding. So like continuous authentication, several works are there which have exploited radio front-end features like the local oscillator drifts to basically identify a device, and then they have also used the CSI information. In the CSI, they have used different strategies to use both the amplitude information and the phase information. So all this information have basically been used to design some sort of for continuous authentication. Next, we have secret key generation. So secret key generation have also been very well studies. There have been some very simple studies like based on RSS, receive signal strength, because that is readily available with the available platform. But RSS is very unstable. So that is the problem. Then again we have the mobility. So with mobility, not only the stability of the captured data reduces, but also we have another factors which affects is the coherence time. For instance, if you are looking into the secret key generation, so for secret key generation, what we are talking about, Alice should send a sufficient number of probe packets to Bob, and Bob should also send a sufficient number of probe packets to Alice, so that both can get an estimate of the channel between the Alice and Bob. And this probing packets transmission to and fro should happen within the coherence time, because if it will happen after the coherence time, the channel will change. Then the keys which will be generated using this information will be entirely different on the two sides, and then it will not make any sense. So that is one of the biggest challenge which we are facing at present, to actually transmit and receive sufficient number of probe packets within the coherence time. Apart from that, another challenge is that one of the node should be in the monitor mode. Means suppose Alice is transmitting the probe packet, so Bob should be in the monitor mode, and then suddenly Bob should transmit and then Alice should go into the monitor node. So this role reversal, so it also takes some time when you go into the real world. So we need to do not only significant exchanges of significant number of probe packets between two entities, but also do the role reversal within the coherence time. So that is a very challenging task. So, and next, this physical layer security has also been used for Sybil attack detection. So this is actually Sybil attack detection and anti-eavesdropping solution are the two most possible solutions which we can easily, means looks easy to design, and it's actually easier to design compared to the above two framework. Sybil attack detection is basically exploit the RSS, receive signal strength value, because RSS receive signal strength can be easily quantify the localization aspect. So it's simply dependent on the distance of the node or the position of the node where it is located. So if suppose we have a given node who just virtually creates a large number of nodes, and all those virtual nodes are bombarding some sort of packets or trying to create a denial of service sort of scenarios. So in that case, although they are doing these things, denial of service scenario, but we can easily identify them because all of these virtual nodes will be having the same RSS value. Even if they are using some sort of power adaptation in schemes, we can also detect that. So that is also easy. So that task can be easily performed, Sybil attack detection. Next is the anti-eavesdropping, so which I just talked about few minutes ago. So it's about secure precoding, means the mapping of symbol and bit scrambling. So what are the challenges of all the works which have been done? So first is the radios which are available do not provide us the flexibility to actually capture the data, because they are binary in nature. We cannot change the firmware. So that is one of the major limitations. So what is the solution? We need to go for the SDRs. And as when we are looking into the SDRs, so first thing is that it will be a very costly solution. Second, the form factor. In some of the use cases, it will not be possible to deploy SDRs. Like for instance, if we consider the use case of a nano drones, so there it will not be possible to use SDRs. So next is the mobility effect, because when the thing starts to move, we are facing constraint in terms of the coherence time. Another is the other thing is the role reversal. That is also one of the challenging thing. Then the other factors are the poor dynamic range, limited bandwidth, the high power consumption, and the frequency ranges. So all these things basically limits the application or even the deployment of physical layer security solutions into onto the product side. So there are a lot of challenges. So the first challenges which means in each steps there are challenges. So first step is how we can do these 5-layer feature extraction, like suppose the CSI extraction and all those things, without using SDRs. So we looked some of the off-the-shelf solutions which are low cost and has a good form factor that can be easily used in all our use cases. So that is the major problem which we'll be tackling into this presentation. So how to perform this physical layer feature extraction. So next Govind will basically highlight on this aspect, the different modules on which.
Yeah. So we understood like why SDR cannot be the obvious choice to integrate all of these solutions, all of these schemes in the use case. So because of the cost, because of the form factor, because of the power consumption, and it doesn't have the good dynamic range because we cannot cover complete spectrum, and plus the precision we don't get, because with the SDR we cannot get the same kind of precision what we can get with off-the-shelf commercial hardwares. Okay, so now to split this problem statement, so now how to extract those features with off-the-shelf commercial hardwares. So that can be any radio. I mean, it can be Wi-Fi, Bluetooth, 15.4, LTE. It can be any other short range or long range hardware platforms. So what we did is like, I mean, we are kind of benchmarking all of these radios in our use cases, in our platforms, which is like phone use case and the drone use case. And what we are doing is we are creating a monitoring framework to get all of these radio measurements so that we can basically implement all the schemes that are already available today in the literature. So if you see the green area, so this is like physical layer parameter monitoring module. So if you see, this is the high level stack of whatever the use cases I explained earlier. So for both use cases, the high level stacks look like same. So in the PLPM, so what we gonna do or what we are doing for our benchmarking, like we are categorizing different RF parameters, different characteristics, and just figuring out, classifying which radio can cater what kind of characteristics, what kind of impairments, what kind of phi attributes. So we have come up with this, I mean, as part of benchmarking, so we are benchmarking SDRs, we are benchmarking different radios. So I'll talk about the framework like Nexmon, Athros, ESP, and there is for short range for Bluetooth, Bluetooth 5.1 has like an RF 5340. We'll talk about this. So if you see with SDR, we can get RSS, CSI, which is like channel frequency response or channel state response. And we have carrier frequency offset, phase noise, IQ imbalance, clock skew, angle of arrival, angle of departure. And with other commercial hardware, we have limited things. So we'll discuss. So first framework, what we are integrating and for benchmarking is the Nexmon framework. So Nexmon is the C-based framework, patching framework with the Broadcom and Cypress Wi-Fi chipset, and it supports CSI capture, which is like active CSI. When I say active CSI, then there should be some real-time active traffic so that the reception of that active traffic can be captured as a raw IQ sample. And apart from that, we can get the RSS. So how it works is like, so we need to basically do the firmware modification. So we need to stitch the firmware with this patching framework, which is like developed for research. And so there is a template RAM, and the raw IQ capture is basically DMA'd from template RAM to template RAM, and then finally as a UDP packet it is being sent from firmware to host. And this is how our benchmarking setup look like. So what we are doing is we are since Broadcom chipset is readily available in Raspberry Pi, so we are using Raspberry Pi 3B Plus, and we are using this topology to get the CSI data, RSS data, so that we can basically benchmark and see if that is really meeting to our expectation for implementation of those schemes. So this is the one which we captured for our benchmarking, in our benchmarking setup. So you can see this is ST20 CSI DUM, and we have amplitude versus subcarrier, phase versus subcarrier, which is channel frequency response, and these are like various scenarios. We didn't brought much mobility aspect, but in coming days we'll be doing a lot of experiments with mobility and doing things. Another one is the ESP CSI. So ESP32, I think everyone who is working in IoT will be familiar with the ESP32. So ESP32 is a series of low cost, low power system on chip microcontroller, which is like Extensa architecture. Now they are giving with RISC-V architecture, and that has integrated Wi-Fi and Bluetooth integrated in the same SoC. And with this, we can do a lot of Wi-Fi and Bluetooth coexistence and getting all of those attributes. So this is the high-level block diagram of ESP. So we can see that we have a Wi-Fi digital baseband, RF front end, we have Bluetooth digital baseband and Bluetooth RF front end. So in our setup, we are capturing the active CSI, we are capturing the passive CSI. So with active CSI can be on either access point mode or it can be on the station mode. So unfortunately, it is not supported with the ad hoc IBSS, which is basically being used in the mesh network or mesh point per se. So the packet structure, if you see the CSI header, metadata header is having the RSS, noise floor, the MCS rate that is being transmitted, channel, rate, timestamp, and the RX status, whether the packet got transmitted successfully or it got some error. So then the buffer has the IQ samples. The buffer has the IQ samples for each subcarrier. So this is our monitoring setup for benchmarking. So what we have done is we have connected ESP32 with the mission computer that can be Raspberry Pi or Intel NUC, and we have connected them over UART. And this is a kind of mesh topology. In this mesh topology, we are basically taking this CSI data in a role reversal fashion. So now here the main challenge is how to change the role from station to SAP or like SAP to station and get those data within the coherence time. Because if you don't get the coherence time, the channel is not constant. And whatever the attribute we need to derive keys or to do these schemes for physical layer, that's not going to suffice. So this is the plot. This is like amplitude versus subcarrier, phase versus. So this is CFR and channel impulse response. We have just taken the IFFT of it, and this is the plot. Okay, next, the next benchmarking, what we have done or what we are doing is with the Athros CSI and as well as the spectral scan attribute. So Athros CSI is also one of the popular framework available with Ath9K and Ath10K driver. So supported radios are QCA6174, which is Ath10K based, QCA9884, which is Ath10K based, and there are a couple of legacy devices like Athros AR9580 and that works with OpenWRT firmware. But the problem is those are end of life platforms. So we thought like QCA6174 or like 9884 can be the benchmarking platform. So what we are doing is we are basically integrating these off-the-shelf commercial Wi-Fi platform over PCI, mini PCI or M2 slot, and this is the mesh topology. And in this mesh topology, we are doing the role reversal and capturing the CSI, RSS, all these attributes for our physical layer parameter monitoring module. So next, so how the CSI look like? So the CSI is having the magic data followed by CSI metadata and the CSI buffer and the trailer for terminating the complete CSI dump, because we can get multiple CSI dump because we need to get more dump for key derivation, more dumps for any authentication schemes within the coherence time, so that we can remove some outlier also if it doesn't fit into the coherent time. So this is the dump. And now it has two parts. One is the metadata followed by the payload, which payload is nothing but your IQ samples. In the metadata header, we have some good information that can be used, like capture bandwidth, channel bandwidth, center frequency, and which mode we are using, HT20 or HT40 or VHT80. And we have noise floor also. Another interesting platform, what we are benchmarking is Open Wi-Fi hardware platform. So Open Wi-Fi hardware platform is a SDR platform, but it is not similar to the traditional SDR. So it is first Linux Mac 8.11 compatible full stack Wi-Fi design based on SDR. So the hardware, if you see, it supports bunch of FPGAs with the radio front end. So typically it is Jink, Xilinx FPGA and analog device radio front end. And good thing is we can full-blown Linux stack we can run with Mac 8.11 compatible stack, and we can get those attributes. Only the problem is like it doesn't have good dynamic range, and bit on the MAC layer security also there is some limitations. So this is the capture data which we are doing for benchmarking. So if you see here, so we have at the bottom the IQ capture, the CSI capture with the subcarrier index. So we have amplitude and phase subsequently. And then we have, the good thing is we get the frequency offset. So typically all the previous platforms what we discussed, whatever the CSI and the CFR we are capturing, that is having the CFO compensation. So we don't get the CFO offset. So that is also limiting for some of the scheme that we are developing. So we thought like we can rather try this and figure it out how it is performing. So this is the frequency offset, and how it works is like, so it has a side channel driver in the Linux kernel space, and it has side channel framework in the firmware. The side channel component in the firmware takes the raw IQ and it DMA to the side channel driver, and once the driver has the side channel information, that can be utilized by the user stack, which is like our classical PLPM module that we are constructing for benchmarking. Okay, another thing is like Bluetooth 5.0 introduced a constant tone extension where an optional bit sequence can be contained in the BLE packet, and that can be used for angle of arrival, angle of departure, which is basically based on IQ capture at the receiving side. So we want to use this in phase and quadrilateral phase sampling samples to do this kind of scheme benchmarking, since I think we can utilize the coherence time principle very well, because Bluetooth is very timely controlled transmission between two nodes. So this is something we want to do. This is something in our roadmap which we have not done yet. So this is hopefully I think it will give some line of sight. So now we discussed all of these platforms, but still, I mean, it looks like these platforms are good for some experimentation, for doing the benchmarking, but do they really solving the problem? Do they really, I mean, whatever the limitation we have, are they really addressing? Not 100%. So it's more like it's a continuous work. So we need to benchmark and then implement those schemes and try to minimize constraint one by one. So all of these wireless modules like IWL, which is like Intel-based Wi-Fi module, which uses IWL Wi-Fi driver, which is only available in the older kernel, and it's not like, and the availability is end of life. The Broadcom module, we can get it for benchmarking. The Athros, the Ath9K based modules are also end of life. QCA6174, QCA9884 are also like, I mean, still available. So that is something we can try to integrate in our use cases. And then ESP32 is good one, so which is, I think probably we are going to continue. And the Nordic one, which is like to be used for the BLE constant tone extension for IQ sampling. So we need to evaluate, but the thing is we need to do a lot of firmware modification to retrieve this data. So with this, I would like Anshul to summarize and
okay, so at present we are basically, so our first job was to go step by step to basically look into all the impediments which we are basically facing. So the first problem was how to extract those features. So we have now identified some of the solutions which we can basically use to basically capture those physical layer features. So now after capturing those features, we need to do the next task is basically the signal processing aspects. How to basically extract the uniqueness from those features. So this is the thing which we are basically using. At present, we basically have one scheme, which is, I think we will get very soon one of the solutions based on the RSS based receive signal strength. But that scheme is not, perfectly can be deployed for all the scenarios. So that scheme we are basically just to start with, to build upon. So we have basically looked into a very static case where all the nodes are basically deployed and they are sufficiently apart. So we need to check whether we can basically authenticate them based on those RSS values. So that we have available. So now next task will be basically to look into this mobility aspect and basically perform the signal processing, because after, suppose for example, if we are looking into the case of key generation, so the first task is obviously the physical layer features extraction. But suppose we get the CSI information. From the CSI information we have the amplitude and the phase information of the respective channel. So from that, now the next task will be to basically synchronize them, because it's very important that both the two legitimate users who are basically using that information to generate the keys should synchronize them from the very first step, and it start from the instant at which we are doing the sampling. So that should be perfectly synchronized. After the sampling, we need to perform a quantization, and we need to look that the results which we will obtain after the quantization, the bit sequence, that will not be perfectly matched even if we do everything in a perfect synchronization. So we need to do some sort of error correcting codes, or even some sort of reconciliation reconciliation method has to be deployed to see that both the keys are matching. So then we will get a symmetric key framework. But there is another challenge. The challenge is that in some cases it might be possible that the channel is not random in itself. So that is one of the solutions, because if we suppose in this sort of scenarios, if we are collecting the CSI between, suppose in this seminar hall we are collecting the CSI, it will be very good. Means the channel will be highly random due to the multipath and all those effects. But if we suppose we go into the, for instance, rural areas, so there the channel will not be that much random. So in that case, we need to think of some other features like the device-based features or something like the RFA front-weight features, so they can complement and enhance the randomness onto those features. So we need to look into this aspect also. So going on to this, so this is basically, so in this presentation, our main job was to just highlight the challenges which we face while we actually started to look into the implementation side of the physical layer security solutions. So and we basically took one of the problem, that is how to extract those features. So we have now some of the modules, and now we will be moving ahead with basically doing the signal processing part of that, so that we can come up with some of the solutions which can actually go into our product side. So this is, so next is the problem which I just basically highlighted you all. So there are a lot of challenges. Actually, unfortunately, we presented a lot of challenges than the solutions. So at present we have just a solution how to capture those data. So next we need to build upon that and move forward. So if anybody of you have some idea to basically how to work upon that, we are very happy to collaborate with, and please free to contact us. We will be very happy if you all can come up with any idea, so that we can develop these solutions and take it to the next level. Thank you.